Hello, Advanced Algebra 2. Welcome to the Concept 24 notes looking at the natural base e and its involvement in exponential functions. So let's start by talking about this natural base e. So the history of math is marked by the discovery of special numbers, such as pi, that's the ratio of the circumference of a circle to its diameter, and I. So pi was a discovery. I was a development. Another special number that has been discovered is denoted by the letter E. And notice it's like a lowercase cursive letter. This number is called the natural base E because it occurs in many exponential situations, things that are raised to the power and this base emerges. It's also called the Euler number after its discoverer, Leonhard Euler, who was a Swiss mathematician. So one way to think of the number e, which is approximately 2.72, just like pi is approximately 3.14, the Euler number is irrational, and so its decimal portion keeps going, but we round it to approximately 2.72. It also is programmed into your calculator, so you can see the E button, which is along the left-hand side of your calculator, just above the LN key. So one way to think of the natural base E is what Euler did. Euler asked the question, if I start with an amount of 1 and increase that amount by 100% compounded as many times as possible within a certain amount of time, what will I get? So that means you've spread that compound interest, if you will, or proportion the amount over a certain period of time as many times as possible. What number will I get? Well, we get 2.72. Seems a little strange. So let's look at it this way. Let's think in terms of money. So compounding interest. Remember from our last concept, we have this formula for interest that is compounded periodically. And so we'll think in terms of money for this situation, but we can also just think in terms of a number. So our amount equals our beginning amount, our principal, times 1 plus our rate, our percent, divided by the number of times that our amount is being compounded within a bigger time amount, and that in that case it's t, it's number of years. So the question in terms of money is, if you invest $1 at 100% annual interest for a year, what's the most money that you can make as you compound it as many times as possible? So 1 will be our P, our principal. Our rate is 100%, and that is just a 1 in decimal form. And then t is also 1. So lots of 1s. Our n, our amount of times that we're going to compound it, will change. All right, look at this table. Okay, so we have the frequency of compounding interest, number of times that it's calculated in a year, the formula, and then the dollar value. So we'll think of it in terms of dollars, but we could just also think of it as a number. So annually, if we compound that 100% interest once, we will add $1 to our beginning $1 and end up with 2 or $2. Now, if we compound it semi-annually, so that means twice a year, so we spread out that 100% interest twice, then we'll get a little bit more. We'll end up with 2.25. Quarterly, that would mean compounding it 4 times, so our n value would change to 4. Our power changes to 4 times 1. So now our amount is 2.44, and I'm rounding to hundredths place, because typically that's what we round the Euler number to, natural base E. Now weekly, our n value changes to 52, so we're spreading out this 100% interest. We're cutting it up into little bits and compounding it again and again. So you can see our amount is increasing, not by a huge number, but by a little bit. Hourly, that would mean compounding that 100% interest over the year 8,760 times. So we spread it into those little pieces and compound it. So now you can see every minute that would be 525,600 times within a year, and we're getting very close to that 2.72 number. every second would be 31,536,000 times that 100% is kind of bits is spread over that year. So we could keep going, but we would just get closer and closer to that 2.72 number. And so we can think in terms of money, or we can just think in terms of numbers. So our base E is approximately 2.72, and it just occurs in many exponential growth and decay situations. It's called Euler's number, or the natural base E. And you have a key on any scientific calculator that will generate that for you. So when you have a problem with the number natural base E in it, use the E key. So let's just do some little simplifying of the natural base E. So it functions a lot like a variable. If you have E squared times E to the 5th, that would be E to the 7th. And then you could approximate that on your calculator and get about 1097. Now 12e to the 4th divided by 3e to the 3rd, we can divide the 12 by 3, which is 4, and then subtract our exponents. So 4 times e, and that is approximately 10.9. And then finally, 5e to the negative 3x power squared, we need to square our 5, which is 25, and then we would just multiply our powers there, and that's all that we could do with that problem because we don't know what x is. So just a few problems practicing properties with that natural base. Now let's look at the parent function of the graph of y equals an exponential function with the natural base e. So a function in the form y equals some number, some beginning amount a times base e raised to the r times x is called a natural base exponential function. When a is greater than 0, and I'll just write it there for you, r is a multiplier. When a is greater than 0, it's positive, and r is also positive, then we have an exponential growth situation like the graph on the left. When a is positive, or our beginning amount is positive, but the r value is negative, then we have an exponential decay. And if you think about what's happening mathematically with that power, e raised to a negative power, you'll understand why that's exponential decay, because that would be a value that is less than 1. So we have these basic graphs, y equals 1 times e to the positive 1x, and it has these points, 0, 1, and then the point 1, the e value. It rises as you look at it left to right. On the right, we have a situation of decay, and notice that that r value, the multiplier by our exponent x, is negative. So if we have positive r value in our natural base exponential function, that's growth, and if we have a negative r value multiplying by our power, then we have a situation of decay. All right, so let's look at these. Let's tell whether we've got growth or decay and graph them. So y equals 3 times e to the positive x. So our r value is positive 1, so we have a situation of growth. Our beginning amount will be 3. So we'll just plug in our typical values of negative 2 to positive 2 for x. And then putting those in the equation for x, I'm just rounding to tenths place when I get a decimal answer. All right, I need lots of positive space. So I'm going to carefully plot those points. So I'm off graph a little with the 2, but I just show that my exponential curve shoots straight up. Notice that it goes up against the x-axis but does not cross it. So my domain will be all real numbers, and my range will be all the y's that are greater than 0. Now looking at b, notice we have a negative r value, so that's going to cause that base to be less than 1. So this is a situation of exponential decay with our natural base exponential function. We'll still put in negative 2 to positive 2 for our x values, and then just put that on our calculator for our y values. Draw your xy axis and label a scale, and then just carefully plot those points, knowing that with the curve, when you connect those points, it will fall as you look at it left to right. But again, it will go right up against that asymptote of the x-axis. It will not cross it. because there's no value that we can raise e to that will make it just go away and become 0. Our domain's all real numbers, and our range is the same, greater than 0. All right, just becoming familiar with the natural base exponential functions of growth and decay, and then how we can plot those and what they look like. Now, let's talk about some real-life applications. So when interest, compounded interest, is compounded continuously, then the amount A in an account after so many years is given by this formula and involves the base E. A equals P times the natural base E raised to the R times T, where P is the principal, R is the annual interest rate as a decimal, and T is the number of years. So you will know to use this formula rather than the periodic or interest that's compounded periodically formula that we learned prior to this one, because you'll see the phrase compounded continuously. That's when you use the base E. So you deposit $4,250 in an account. That's our principal. That pays 5% annual interest, so that is our rate. And then as a decimal, it's 0.05. And then we need to find the balance after a year, 5 years, and 10 years, noting that it has been compounded continuously. So we will use this base E formula. So after 1 year, that means that our T, our time value, is 1. So putting that in the calculator, we will round to cents. And so if you're not given instructions on what to round a money amount, a dollar amount, or always round to cents place. That's the second decimal place. All right, after 5 years, at just 5% interest, not adding anything in, so now in our formula, our T value will change to 5. That money will become $5,457.11. And then after 10 years in the formula, our T value changes to 10. And the account will earn $7,007.07 just by putting the money in to an account, not touching it, and letting that interest accrue. So that is a good real-life application for our natural base E when interest is compounded continuously. You and your friend each have accounts that earn annual interest compounded continuously. So the balance, A in dollars, of your account over so many years, T, can be modeled by that equation. The graph shows the balance of your friend's account. So let's just label, we have our friend's account there, and yours is this formula. So we're just going to compare things from your formula and your friend's graph. Which account has a greater principal? So you know that's the starting amount. So we can look at the graph where it's crossing when our time is 0. So that would be 4,000. That's beginning amount. And then if you look at your formula, that amount in the P position, principal, is 4,500. So yours has a greater principal starting amount. Which has a greater balance after 10 years? So we can read the graph for your friends, and when we read the graph, it looks like after 10 years, your friend's account will be worth $7,000. And then with your account, we can just plug in 7 for T. And then this will reveal who has the higher interest. And it looks like your friend's account does, because your friend started with a smaller amount, but the account accrued more and has earned more in 10 years than yours have. So your friend's account has earned more. All right, that concludes just an explanation of the natural base E and a look at its graph and some real-life applications.